So yes, so we have already discussed till kinematics. Okay, we have seen kinematics, we have seen how velocities can be dealt with, right? Now it's high time when we can start discussing about the forces. How does a robot behaves with an external force? That is the first. How the robot behaves with its own weights, that is already associated with its length. Okay, and also if at all it is in motion, does moment of inertia of each link also has some role. Okay, so dealing individually each one of them. First, dealing with the forces, external or internal. If it is not moving, we call it statics. Okay, so we'll start with statics now. Okay, so let us just start with this. uh, Statics as such is a huge thing that can be covered over here, but yes, if at all, let us say you have a robot which looks like this. Okay, this is just a pictorial I am drawing. Okay, you mounted on the ground, first axis of rotation, second one, third one. That is the age old figure for you now. Okay, if at all it is acted by an external force. Okay, let us say if it is lifting a weight which may be acting downward, or some external force that acts on the end effector. Okay, at some point of the end effector, or the just at the end effector point where you normally have the flange center of the industrial robot. Okay, so if at all you apply any force over there, what influence will it have at each of its joint? Okay, so yes, we'll start with one of the very popular method which is known as principle of virtual work. Okay, that assumes that robot is not moving. I assume a small displacement that might have occurred because of this force from the position where I want to do the analysis. Okay, so let us say there is a small displacement which has happened here, a small displacement probably that has happened here also, and maybe some displacement which is happening over here. Okay, it has further moved to a new value. Okay, so this is a small displacement, I call it delta theta. Okay, and mind it, delta theta is not just delta theta, it is an array of all delta thetas. If it is a three jointed robot, it is delta theta 1, delta theta 2 and delta theta 3. Okay, so it is that. And similarly, and also assume that this has an effect of creating torques and forces. Generalized torque, I call it force and torque. Okay, so that is happening over here. So it is tau 3, tau 1, tau 2. Okay, so if it is like that, again this also is an array. Okay, so it is in this form, tau 1, tau 2, tau 3. Okay, actually I have put a transpose over here because it actually is in this form, tau 1, tau 2, tau 3, so that transpose becomes this. Okay, transpose becomes this. Now what is this term? Product of this and this. What does this say? Torque into displacement, force into displacement. It is a age old stuff. Okay, so that is now, this is the work done by the forces on the robot. Okay, so this is what is the work done on the robot. Okay, so this is what is at the joint level. If I see, that is the outcome of the external force, outcome of the external force. Okay, at the joint level. Okay, then if at all I see it from a different perspective, from the input side of it. Okay, from the input side of it. So what does this say? Again, WA is the wrench. What is wrench? Wrench is a combination of external moment and forces. Okay, external moment and forces. This again is a vector. This again is a vector. So you have nx, ny and z. These three are the moments, and then you have forces fx, fy and fz. So all together in a single matrix. Again, if I do transpose on that, that means I am just arranging it in a this manner. Okay, again it has Same, if it is delta x, what does this delta x say? This delta x is now displacements, both angular as well as translational. Okay, so again it is in this form, angular displacement at the end. Okay, so you can call it simply some displacements that is happening here. Okay, join angle end effector angular displacements. Okay, ax, ay, az, these are angular displacements over here. And similarly you have displacements like delta x, delta y and delta z. Overall it is already in this manner. Okay, so if I take product of these two, what does this give? Moment, angular displacement, moment, angular displacement, moment, angular displacement, and force, linear displacement, force, linear displacement, force, linear displacement. If I take the product of these two, this effectively tells me how much work that has been done on the robot by this external force. Is it not? So this is from the input side of it. Okay, from the input side of the robot, and this is the effect. This is what is happening. So that is the output. So this is a small definition of principle of virtual work also, that you know already since long time in engineering mechanics. Okay, so this is in compact manner I can write it as wrench is a combination of moment and forces external, okay, vector of moment and forces called as wrench. Tau is joint torques, delta is delta x is end effector angular and linear displacements, delta theta is joint displacement. This is what it is. So effectively this is the work done on the robot by the external forces. So this is input work done and this is the output. Okay, so work done on the robot should be equal to work done that is done by the robot. Okay, so effectively it is like this. So equating these two, okay, and substituting something which we already know now. Okay, this is what is from the exact definition of Jacobian. Jacobian relates two rates. Okay, it says delta x by delta t should be equal to j delta theta by delta t. So rates. Okay, this is Cartesian rate, this is joint rate. Both are clubbed by this term which is known as Jacobian. Okay, this is what is Jacobian. This is from the definition. Okay, sorry, this is delta t. Okay, so this can be written as a partial displacements, can be written as this. Okay, now I substitute this to this original equation. In case of delta x, I simply substitute this, it gives me this. Okay, so I just substituted delta x over here and I got this, and if I cancel them out, so it simply can become this. So this is a relation between the wrench that is acting from outside and torque that is as an effect of that this torque is generated on the robot by this external force. Okay, if I take transpose on both the sides, I can write it like this. Okay, transpose, taking transpose both the sides, you can write it like this. Is it not? Hope you remember that transpose formula. Okay, A transpose B whole transpose is equal to B transpose A. So that is what is put here. Got it? Okay. So yes, so now this is a standard relation that relates if you have a robot, okay, you have a wrench that is acting from external. This is a vector of moments and forces, that is called wrench, and torque that is generated over here. Okay, tau 1. So this is the effect. Both are related now by Jacobian transpose. So Jacobian not only will relate joint displacement and joint end effector displacement, okay, it relates forces in this manner. forces and torques in this manner. Okay, so this is one of the very important benchmark equation that is going to bother you from now on. Okay, so this is another role of Jacobian, that is in terms of statics. Okay, so this is what we'll be using in controls and many other robot aspects. Okay, okay. So now moving ahead, can we do the same? Can we do the same statics of joint force due to gravity? Okay, what is this? This was due to the external wrench. Okay, now I want to analyze what will be the effect of forces that is arising due to the masses which is associated with each link. Okay, they are all in a serial chain from inward to outward. Okay, they are all like this. So this acts like this. Okay, this mass also acts like this. Each and every mass will act like this. Okay, again I am doing static analysis. That means these masses are not moving. Even if it is moving, it is negligibly small. So that is the case. So we can easily ignore the velocity and acceleration portion of it. Forces, those are generated due to velocity and acceleration. Okay, so that is what I am ignoring. I am just analyzing this statically. Okay, so now this is approach when you go outward to inward. Okay, that means the joint, let us start with one of the joint, that is EI vector. Okay, EI vector, this is the ith joint. Okay, so this is what is holding your link of center of gravity placed at Ci. Ci is the position of center of gravity. Okay, so this will create some moment over here. This second link will also create, let us say if it is frozen at this point. Okay, frozen at this point. Next is all frozen. So robot is static in its own position now. Okay, none of the joints are moving. Brakes are applied to say. So how much will be the torque at this location? Okay, so torque over here will be the sum of all the torques which comes after this joint. Is it not? The joint torque over here will be resultant of torque arise due to masses that come after this joint. Is it not? So torque caused due to this mass, torque caused due to this mass, torque caused due to this mass, finally till the end effector, and even the tool. Okay, if at all it is mounted. So this I assume it is a part of this. Okay, for now. Okay, so this is what is well known. So this is forward kinematic transformation matrix for the ith frame, this frame with respect to the robot base is given by, okay, with respect to the robot frame is given by Ti. It is, this is what, this is orientation of the frame that is attached to this, and OI plus 1. OI plus 1. Why not OI? Frame which is attached to link I is OI plus 1, if you remember that. Okay, so ground frame you have first link, zeroth frame link 1. Okay, link 1 has frame 1 attaching link 2, link 2 has next frame, and so on and so forth, if you remember that. So that is what is followed here also. Okay, so this is OI plus 1. Okay, so this is a general structure of any link transformation matrix point that is holding over here, that is over here. Okay, so that is what is the transformation matrix. Okay, now this has many information that is hidden to it. First one is the position of this. Just a sec, let me clean it off a bit. Okay, done. So now this is OI plus 1. So this is given over here. that is the frame which is attached to link I, okay, I plus 1th frame, that location is there. And this orientation is basically orientation of the frame which is here, okay. So it has its own z axis which is pointing towards the along the axis of rotation for the next link, okay. So that is what is there, okay. Now can I write next line? You just see it carefully, okay. This has again many information, okay. What is di? What is di? It is the position of center of gravity of the ith link with respect to link I minus 1. So it is effectively this vector, okay. So this is what is di, got it. So this is what is di. As a vector it is there, and this is well known in its own frame. Let us say you have a bar, okay. So you very well know it has its own center of gravity, okay. And if it is a solid bar, you very well know if this is the frame which is attached to this block, okay. So you already know this vector di. If this is link I, okay, if this is link I, you already know di because you know the center of gravity of each link in its own frame. So this is the frame which is attached to the link, okay. So you already know di, okay, with respect to its own frame, not globally, okay. So if I rotate that frame with respect to this frame, that is the ground frame O1, okay, first frame, so you have to multiply this by qi. This is the orientation matrix. So you have to multiply this to express di in terms of robot base, okay. So this is with respect to base transformation. This is the rotation matrix that we already know through forward kinematic transformation. Di is known in its own frame, so I just rotated that with respect to the base so as to obtain this. Now this vector di is expressed with respect to the robot base. In this frame I am now expressing it. So now this vector is known in this frame, got it. So di is known, okay. So this is known. You already know oi. How? Similarly, the way we got oi plus 1, we got oi plus 1 by this transformation matrix. The transformation matrix that comes for this link I minus 1, will have position for OI, is it not? So that will be also known. So OI is also known, DI is now expressed. If I take the sum, I can obtain CI. What is CI? CI is the vector that connects base to the center of gravity vector, center of gravity of ith link. Clear? So that is what. So now I know everything. Okay, I have all the information with me. Okay, so let us move ahead now. So this is the complete equation. What does this say? I'll repeat once again. Di was already known in its own frame. I used rotation matrix from this, okay, and expressed this vector di vector in base frame. Now OI is obtained by the link which is here, okay, that is I minus 1th link, okay. If I take transformation matrix of that, that will have this also. So I can obtain, if this is known and this is known, so I can obtain center of gravity vector. So this is what is done, okay. Now why this is so important? Because one by one I am trying to get the distances, this vector, okay, the vector that connects the center of gravity from the joint which is in consideration, okay, from the joint which is in consideration. I want to find out torque which is here. Okay, so I have done this. Similarly, I can find out Ci plus 1 the way I did for ith link. Okay, this is for the ith link. I can do for I plus 1 and I can do for I plus 2 and so on and so forth till the last link. Okay, so this is also found out in a similar manner. You know this, you know this, now you can find out this. So that was repeated one after the other, and this is how we can find out dik. So this is what is done. The intermediate vectors dik, it joins the origin of the ith link to the center of gravity of the kth link. If I is in consideration, I plus 1, I plus 2, so there is a variable which is k that starts from I and ends to the nth link. So it starts from I, goes forward manner till nth link. Okay, so all the links that comes after this join, that only counts. Okay, so that is what is done iteratively from inward to outward side. Got it? Okay, so now I have all those distances. This one is known, this is known, this is known, all are known. Okay, now what I am willing to do now, I know the vector, I know the vector, position vector. I also know the force that is acting. What is that? If it is ith link, this one is I plus 1, so it will be mi plus 1, that is mass of this link into acceleration due to gravity. This is a vector. Okay, acceleration due to gravity is a vector. So this effectively is the force vector, force due to gravity for I plus 1th link. Is it not? For I plus 1th link. So that is acting like this. This position vector is known. If force vector and position vector is known, you know how to calculate the moment that is acting over here. How much is that? It is simply this. Is it not? Mi is a scalar quantity. Okay, mi is a scalar. So it is just a cross product of this and this. Is it not? So it is r cross f. That is the age old equation, that is for the moment you have been doing. It is cross product of position vector and the force vector. So that will give you the moment that is acting over here. That is, mind it, this is not aligned to E. Okay, so it is now what I am doing. So total moment that is acting over here due to all the links will be summation of all. Is it not? Just a sec. So it will be summation of all the vectors sum. Okay, so if it is an I due to this mass plus an I plus 1 due to this mass and so on so forth, finally it will be for the n, that is the moment due to the, so moment due to this one. Okay, so sum of all moment will be the resultant moment acting at the ith joint. Okay, so this joint. Okay, so that is just the moment. Okay, that is just the moment, it is not torque. So how much is torque? Let me do that again. So what will be that? So if this is the moment, if I project that along the axis vector, that is ei vector. What is ei? Ei is the unit vector that is directed along the axis. If I take dot product with that, that is the torque. So torque is nothing but the projection of moment along the axis of rotation. I repeat, torque is moment projected along the axis of rotation. Over here it is ei is the axis of rotation. So dot product is nothing but it is a technique of projecting a vector in along that direction. Okay, so that is what is the total torque that acts along tau I. So this is tau I. Okay, and this is because of all the masses that comes after this. Okay, now for the first one it will be E1, so it will be 0 0 1. You know rotation axis is always along z axis. So for the first one it is like this. For the next one, you can, I have already discussed how can we obtain different EI earlier. Okay, that is from the forward kinematic transformation matrix. Let me just do it here. Okay, so forward kinematic transformation matrix for A1 will have E1, is it not? Sir, excuse me. Yes, please. Sir, why not we are taking into account previous bit for torque and see what happens. Let me just clarify this one. Okay, just a sec. So if you can see this robot, okay, if you can see this robot, okay, this is like this. So how much will be that? Let me just enlarge myself. Just a sec. Yes. So this is the robot. You can see it clearly. Okay. So how much will be the torque that acts here at this point? It will be due to all the links that comes next to it. Okay. Due to this mass, due to this mass, due to this mass, is it not? So that will act over here. But if I take this joint in consideration, so all the load that comes after this only creates motion over here and moment over here. So moment over here will be due to all the links that comes after this, is it not? So anything before that is not going to create moment over here. Got it? So that is the reason. So moment over here is because of all the links that comes next to this. Moment of over here will be all moment due to all the links that comes next to it. Moment of over here will be due to this. Okay, so maximum moment that you see is at this point. That is taking load of everything that comes next to it. Okay, so that is what in series it is happening. Okay, hope you have understood. Yes, obviously, this is a static analysis. If it is frozen, okay, so that is what is the case of a static system. This is frozen. Anyway, this is just a support for this link. This is just a support. This moment is applying that brake now. This is not moving. So it is creating moment. You can take some example and you can try out with you also. Okay, so rest, nothing is moving here. Okay, nothing is moving here. So you can imagine here, come on. So you can feel it. If you try to move this from here, if you try to move it from here, it will be most difficult, is it not? If you have felt that, you take something like this, okay, and if you hold a simple danda in your hand, a small stick in your hand, okay, the closer you hold it towards the end, easier it is for you to move it, is it not? If you hold it at the end, it becomes very difficult. Why? Because it is carrying all the load that is after this. If you hold it here, it becomes easier, is it not? So that is what is the case even with this. Okay. Okay, so moving ahead now. So this is how we calculate. Now we calculate for all the torques. Okay, so that is why we calculate torque here, torque here, torque here, and combined way we can write. So this is torque is a scalar quantity, moment is not. Okay, moment is vector, whereas torque is projection of a moment along the axis of rotation, and you see there is a dot product that is used here. So effect is a scalar. Okay, so this is actually causing the motion. Moment, okay, moment over here is not causing any motion because you don't have any axis that can rotate. Okay, so this is only responsible that is creating motion. Okay, so now I'll arrange all this in a single matrix like this. Okay, so this is complete gravity torque. So net gravity compensation torque vector is an array of all the torques. Okay, so from T1, T2, T3, T4 till Tn. Okay, so all the torques I have arranged in a matrix form like this, or it can be written as T1, T2, T3 and so on so forth till tau n. So vertically it can be written like this. Got it? So that is what is your torque now. Okay. So that is exactly the thing that I wanted to tell you. So this is the amount of torque which is required at each of its joint, even if the robot is not moving. So because this is a serial robot, okay, it will fall on its own weight. Due to its own weight, it is going to fall. So this is the array of torques that is to be applied at each joint at any static condition so that it doesn't fall. So it is a gravity compensated robot. Okay, that means anywhere you leave it, it will become as if it is in a space. There is no gravity that is acting. So all the torque is because of this gravity. If G itself is zero, it will not fall anyway. Okay, so what I am trying to create now, I am trying to create a moment, a moment, okay, a set of torques that is to be applied at each joint. If I do that, this robot becomes a floating robot and it is cannot be moved in space. Got it? So this is known as gravity compensation torque, and this is what is required for any controller to use this much of torque bare minimum so as to control, make the robot more uh, easy to control. Okay, so that is why. Okay, so this is a static analysis that is doing gravity torque. Okay, earlier what we did, we checked how much is the, if any external force, if it is acting on this robot, how much will be the torque. So net torque that acts on the joint will be sum of, that will be on top of this. So gravity torque is always there. You have to apply this much of torque in order to keep this robot in a particular manner. Okay, and on top of this you have to apply torques that will take care of any external force. Okay, again there will be some dynamic torque also. We'll talk about dynamics later. Due to the motion itself, you have to apply some torque. So there are plenty good number of combination of torque that is acted on the joint at any instant of time. Firstly, this one, that is the gravity compensation torque. Next, if it is loaded with an external force, normally it is, if it is picking an object which is of 100 kgs, so that load is going to create torque at each joint. So that also you have to apply at the joints. Okay, and if it is moving, that dynamic load is also going to come. So that also you will have to apply, and maybe friction and many other things that is to be there. So for that reason controllers are there. Okay, so this is one of the very important benchmark derivation which is that you have done now. Okay, and this is required to make any cobot nowadays so that it becomes compliant. Okay, so anyway we'll talk about that later. Okay, now there are many terms which are associated to statics of the robot. Okay, so we'll talk about that now. So one of the most important term, so these terms are known as kinetostatic measures of for any robot design. Okay, so now let us say you have a robot. Okay, you have a robot. Let us start with just two link robot. Okay, so if it is having first link and you have second link. Okay, so this joint, it is picking up a weight which is over here. So you have a weight length A2, A1. Okay, so is this robot equally capable in each and every space where this robot can go, entire workspace where this robot can go? How do you prefer to pick up a mug which is filled up with water? Okay, do you take it entire hand is stretched and you pick up that bottle? No, you always try to maneuver in the area which is most convenient to you. Is it not? So why you want to keep it always slightly bent? You try to maneuver in the region somewhere over here. Why don't you want to go somewhere over here? Okay, and do the rest, do all your tasks. That means you have some manipulability issues which are over here. Although it can pick up this much load, provided you have enormous amount of torque that is available at the joints, you can do it. Robot is reachable too, but yes, it has some limitation. Again, you must have seen when you do cycling, okay, you try to prefer your pedal, you try to keep your pedal somewhere in the region which is like this. You don't tend to, maximum amount of time you spend is somewhere within this region. Okay, it never works mostly in the extended region, it never works well even over here. Okay, so over here there is some issue, over here again there is some issue, and also if you have to push something in this direction, that is the pedal, okay, obviously it is very difficult to pedal with your knees folded like this, is it not? You tend to be somewhere in the middle of this. That is the reason when you start your bicycle, you try to lift your pedal somewhere in this region. Then you start, because the starting torque is always higher. Okay, so you bring your pedal to this region, push it, and by inertia you can keep it moving. Okay, so that is what I want to talk now. Okay, so that is first definition in this category is called as dexterity of a dexterous robot. So it is ability of a manipulator to reach all the points within the workspace with with all possible configurations of its end effector. What does it mean actually? Let us just start with a planar robot. If it is a 3R robot, 1, 2 and 3 links, okay, it starts somewhere over here with the ground frame X and Y, something like this. Okay, so you now know this is for orientation. First two is for positioning. Okay, so if at all you can go to a point which is sum of lengths of all the three. Okay, you can go to A1 plus A2 plus A3 this distance, okay, but you can orient only in one manner, is it not? You can only be like this. So this tells clearly that you should be able to orient yourself in all the possible manner. That means dexterous space for this robot will be sum of A1 and A2 only. That means A3 is only for orientation. So last link is only used for orient. This is in case of planar 3R. Similar would be the definition even in case of spatial robot. Okay, got it? So with all the possible orientation of its end effector, a robot should be able to go. That space is known as dexterous space and can transmit motion and force comfortably. Okay, transmit both motion as well as force. These are the two different things. Now again, okay, we'll talk about this once again in second definition of this. Let us go there now. Okay, okay, now what is this? This is called dexterity. Dexterous space and dexterity is different. It is defined, it is quantified as a good manipulability value, and this value is given by JJ transpose. JJ transpose determinant. So if J is the Jacobian, J transpose times of that will create a square matrix. You can take matrix like this. If you take square root of this, the value that you get is called as dexterity value of that. So that is given by WD. Okay, over here I have written WM, there is a special reason for that. Okay, I'll just come to that. Okay, so why this is so, where from this value has come, that things will be very clear now. We will deal with one of the example also. Okay, so if it is, let me just complete this two, then we'll come to that. So JJ transpose, what is Jacobian? You already know that. JJ transpose determinant of that, square root of that. Okay, so that will give you a value that is known as manipulability, a good value, good manipulability value. Okay, now for redundant manipulator, non-redundant. Non-redundant means which one was redundant? Let us say if it is a 7-DOF robot, 7 degrees of freedom robot. In that case, J was not a square matrix, right? It was not a square matrix. You saw that earlier. So it is a non-redundant robot. Why? Because you can only control roll, pitch and yaw, x, y and z for any end effector. But you have 7 inputs, theta 1 to theta 7. So J is not a square and it is a redundant robot. For that it is not valid. For any non-redundant robot, J is a square matrix. J determinant can itself be a square matrix. Okay, matrix is possible. In that case, WD becomes equal to WM. That means manipulability becomes equal to WD, that is dexterity. Okay, a robot may be more dexterous, but it becomes equal to manipulable, good manipulable if both are same. Okay, things will be more clearer now as we move ahead. So let me just move ahead, keep moving now. Okay, so there are different condition number which are associated with this. The ratio of maximum to minimum singular values of this matrix J, okay, maximum and minimum singular values of J is the measure of singularity. Okay, so you saw earlier in case of 2-DOF robot, the matrix became singular if it was fully extended. Okay, if it is fully extended, matrix becomes singular. In that case, you cannot apply any force in this direction. Is it not? If it is fully extended, it cannot apply any force in this direction. But it can have maximum force, maximum velocity in this direction. Just follow me what I am saying. Okay. So, this direction you have maximum velocity and you have zero force in this direction. Okay, that is first thing that you carry away now. I am assuming this arm is fully extended. In fully extended case, your arm is something like this. You cannot apply force in this direction, but you can have maximum velocity for the same angular velocity of one of your joint, that is theta 1 dot. Okay, so V is equal to R omega. You all know this becomes the radius over here, R. So for the same, if R is maximum, V is maximum velocity, peripheral velocity which is here. So you can apply maximum velocity in this direction and minimum force in this location. Okay, now if it is fully infolded, okay, if it is fully folded inside, okay, let us say your robot reaches somewhere like this. Okay, in this case what happens? In this case what happens? It can apply less velocity in this direction, whereas it can have more force in this direction. So there is F max in fully enfolded way and V becomes V minimum. Okay, V becomes less, F becomes maximum. That means you have V varying from maximum to minimum, from outside to inside space. Similarly, for the force it is opposite. You have minimum force at the fully stretched condition and maximum at the inside condition. And there is some optimum space that lies somewhere over here. Now you got the philosophy. Why we want to work somewhere in the manipulable region. In the manipulable region, that means you want to have some optimum value of velocity as well as force. So you can move in a better manner, okay, have better movable velocity and as well as you can have better force values, right? You can apply forces in a better way. Okay, so that is the reason you want to be in this location most of the time. Now what is Jacobian? Why did it came to the picture? Jacobian relates what you saw just now, end effector force, and joint torques by Jacobian transpose. Okay, I'll show you that equation that we did just now. this one, okay, this one. So J transpose WE, that is the end effector force, is equal to tau, and it also relates velocities, joint velocities and effector velocity, okay, that is also related by this. That means force, force is related by Jacobian transpose, and velocity is related by Jacobian. Okay, if I combine them together, that is the work done that I want to do. Okay, what I'll have to do, I'll have to take product of these. So that is what is used, and that is why JJ transpose came into picture. Okay, so that probably is in my next slide somewhere. Okay, we'll come to that once again. Okay, so that is why this thing came into picture. That gives you a better picture of velocity and force both in a single thing. Okay, and what it is basically, this itself has something to say. Okay, mathematically also, apart from some physical meaning that we saw as velocity and forces. Okay, JJ transpose has meaning, but it also has some meaning. Okay, that will come later on. So okay, so what we want to do now, so this index, okay, condition number shows how near this value is towards the singular. If a matrix becomes singular, that means you cannot apply any force in any direction. Okay, robot cannot have any force in any direction, so it becomes singular. Okay, so matrix J basically shows the value of this, shows how near it is to the singular. So condition number is a similar number which is associated to Jacobian, and this shows how near it is to the singular matrix. Okay, so okay, so that is the reason this is used as an index to express how better you are in your region where you can show your maximum performance. Okay, so accuracy, dexterity of the robot, these two are described by this index. How closeness it is to the singularity of the robot, so it will give you the picture of both. Okay, closeness to the singularity, as I have showed in case of 3R. Okay, if it is fully stressed, first, second and third, all the links are fully stressed, that means it is singular. Okay, in this case it is not that dexterous because it cannot have all sorts of orientation. That means near to the singularity it will lose its dexterity also. That means this J has lot many things to say. It loses its dexterity, it cannot apply full force, and it can have some values of velocity only, others will not be there. Okay, it can definitely, in fully stressed condition, it can have maximum velocity in this direction, whereas no velocity in this direction. Okay, so yes, it is very much constrained in that case. So that is why we take this as a matrix, as a value, a physical value which is saying so many things. So how close it is to the singularity, how dexterous it is, both can be given by this value. Okay, and that is this value. In case of non-redundant manipulator, both are same, these two become same. Okay, and this is the physical definition of dexterity when it says workspace with all possible orientation. Okay, so these are some important definitions. Okay, we'll come to that more closely now. So manipulability is what? It is capacity to change the pose of the end effector, capacity to change the pose. Pose means position and orientation of end effector of the robot at any given configuration. At any given configuration, whether it can have all sorts of poses. Okay, so it is measure how close it is to the singularity. If it is closer to the singularity, definitely it will be less manipulable. And what gives you the value of that? J. Okay, so now this is some duality that I want to discuss for 2R manipulator. So you see it is given by an ellipse. Okay, so this is what? This is velocity ellipsoid and force ellipsoid. So effectively For 2R manipulator, it is ellipse, not an ellipsoid. For 3R, because it can apply forces in all the direction and velocity in all the direction, it will be ellipsoid. Okay. So what you saw when it is fully stretched condition, okay, let me just show you this one. So what this is showing, it has velocity which is maximum, okay, in this direction. In this direction it can go maximum, okay. And then if it is fully enfolded, velocity can be only in this direction, okay. Velocity can only be in this direction. V becomes V max over here. So you have a range. When this becomes maximum, another one, this becomes maximum. So in between you will have something like an ellipse that says it has more value in this direction, less value in this direction. So gradually this ellipse major axis will reduce this, that if you move from inside to outside, okay, it will be something like this, is it not? So that is what is this velocity ellipsoid. So it changes its shape, okay. So it becomes something like this over here, and it becomes something like this over here, and in between you may have a circle in between when it can apply maximum velocity in both the direction or optimum velocity in both the direction. So that is what is velocity ellipsoid. What about the force? Force ellipsoid is something opposite to that. Okay, that is opposite to that. Why? Because you know, when you have maximum velocity in this direction, you can have maximum force in this direction. How? I'll tell you. Okay. Yes. So yes. So this becomes maximum. Okay. So in this direction you see the maximum force. Okay, if this is maximum over here, force is maximum in this direction. Again, when it is inward folded, you can have V becomes maximum in this direction, whereas force becomes maximum in this direction. Okay. So force ellipsoid is always the same. You must have realized when you have you might be cycling, okay, you can apply maximum thrust to the pedal when it goes at the bottommost portion, okay, and you can apply least force when it is fully enfolded. When your leg is like this, you can apply least amount of force. When your leg is like this, you can apply maximum amount of force. Is it not? So again, you can move with maximum velocity in this direction, is it not? So that is what. So both of them are orthogonal to each other. Both of them are orthogonal to each other. So this is what that we have felt quite a lot of times, but let us now start formalizing that using some mathematical interpretations. Okay, so this is again end effector force ellipsoid. So that is nothing, it is exactly orthogonal to this. So the way it is here, so it will be this direction, it is maximum. This is force ellipsoid. So it is exactly orthogonal to these two. Okay. So now moving ahead now. So general derivation of velocity and force ellipsoid. Ellipsoid because it is easier to visualize in 2D plane, but in case of any 6 degrees of freedom robot or 3 of robot or more which can go spatial, okay. So for that you can see ellipsoid. You can apply force over here, you can apply force in this, you can apply force in this. Overall it becomes an ellipsoid. Okay, so that figure also I'll show just now. So let us just begin with this. So velocity of end effector is given like this. That is related with joint rates like this. You all know this by the definition of Jacobian. Okay, where each one of them are in real number domain. Okay, now. So this is how if you form a circle, if you try to form an equation of a circle of unit radii, it becomes something like this in these two terms. Okay, theta transpose theta dot, Okay, so this becomes equal to 1. This is nothing but equation of a circle of unit radii. Okay, this can be easily derived. This can be easily derived if you just see this, because these are some of the magnitudes of this. Okay, so you can write it like this. It becomes x square plus y square is equal to radius square. So over here it is x, this is y. Okay, so if it is theta 1 theta 2, I can write it as theta 1 theta 2 like this, and theta 1 theta 2 like this. So what is this? So this is nothing but transpose of this is this. Okay, so that is what is written here. So that is theta transpose, and this is theta. So what is this basically? Theta 1 square plus theta 2 square. So what is this? This is nothing but this one. This is nothing but this. If at all, if it is both unity, so it is a unit radii circle. Okay, so you now know this represents a circle in space. Okay, so that is what we want to see. When is this a circle? Okay, so we want to analyze this by a circle equation now. So now we move ahead with this. If I substitute this over here, okay, in this equation, I want to substitute this. Okay, so I can write it like this. So exactly J inverse VE is equal to theta dot. So I can write it here. Similarly, I can write it here. Mathematically, if I keep moving like this, transpose, okay, then this I can club these two inside. Okay, like this. These are some linear algebra terms that I am just doing it. Okay, so V transpose VE. Okay, so now what is this term? Now what is this term? Okay, if I take this as a separate entity, that is A, so this is what is this? What does this represent? Okay, so now in case of generic value of velocity, when V is x, it is not a unidirectional velocity, a generic velocity in all the directions. So what does this represent? And what is this? This is nothing but a symmetric matrix. You know, it is a square matrix also, and it is positive definite matrix. Okay, it is always a positive matrix. Determinant of this will be always a positive value. Okay, so that is just the property of this. Now, okay, so eigenvalues of this will represent the, so you can find out the eigenvalues of this as well as eigenvectors of this. What does this say basically? These are some mathematical derivations. Okay, this makes things more clear to visualize why force and velocity behaved like the way we saw it just now, why we are able to apply maximum force in one way and least amount of velocity in the same direction. Okay, so now things will be more clearer. Okay, so this time you have, if you take, what are these lambdas? These are nothing but eigenvalues of this matrix. Okay, eigenvalues. If you take square root of those, this is basically the axes of your ellipsoid. Okay, now what are eigenvectors of this? These are these vectors which are the direction of the axis of this ellipsoid. Okay, so this is so interesting that you came up with an expression which clearly tells you the direction and the magnitude. Okay, direction where you can apply with a particular magnitude for the forces. Okay, so yes, now you have two things. First, this is because you have velocity you have taken here. Okay, you will get something velocities which are behaving in all the three directions. So this is a manipulability ellipsoid which shows you velocity along three directions. Okay, if at all you have to do analysis for forces, how will you go for it? You have to use the equation. Now I have used equation for velocity. Okay, I have started with velocity equation. Okay, so this was the velocity equation I have used, okay, that related velocity and the joint rates. If you started off with um, wrench and the joint torque, okay, you will get a similar expression. Only thing you will be associated with Jacobian transpose then, okay, and you will get the force ellipsoid in that case, okay. So if A is equal to JJ transpose inverse, so if A is equal to this for velocity, it becomes this for inverse of that. That is, in case of force, you get A as this, and you see both are orthogonal to each other. If velocity ellipsoid is like this, force ellipsoid will be something like this, okay, and gives a force ellipsoid resulting from the unit sphere of joint forces and torque. We started with unit sphere of velocities. This time it will be for forces. So yes, these can be visualized only with little bit of workaround with that. I don't assume you get 100% right at the moment, but mathematically things you can follow very easily. Reason behind this is yet to be discovered by you all. Okay, so I assume you will do some exercise. Definitely this is not as important as of now, but yes, this gives you a very clear picture why we use something like this while we did manipulability analysis. Okay, why a robot is able to apply more force in one direction and other velocity in the other direction. Okay, extremes we can analyze. Okay, we also could feel we ourselves are better comfortable in this region of the workspace. So these three we can analyze when we do paddling, we do manipulate anything in day-to-day life. But yes, entire picture of this mathematically can be obtained something like this. Okay, so these are some of the vector way of writing equation of a circle. Okay, this might be a bit new to you, but yes, it is like this. Okay, so I think there are some takeaway from this manipulability and force ellipsoid. The circular shape would mean that end effector is equally manipulable in all the directions. If at all it has a shape like this over here, it has a shape like this here. So if it is having this shape over here, that means it is equally manipulable in all the direction. You can go with same velocity in all the direction. It can have same forces in all the direction also. If it is a circle for velocity, it will be circle for sphere also. Oh, so forces also. Okay. This defines the end effector motion capabilities, and it captures how close the robot is to the singularity. If this is at the end, this ellipse will become something like a straight line. It will be fully collapsed condition, and then your robot is in singular condition. Similarly, if it is fully enfolded, you will have velocity of ellipsoid something like this. Okay, so that is what is another case, another extreme where your robot is singular too. Okay, so this clearly gives you that picture as well, how close it is to the singularity. Okay, how better you are manipulable. Same thing if you see for the force ellipsoid, it gives you the principal axis. Okay, principal axis where you can see the maximum force. Okay, let us say you have to, your robot is in this configuration. In this configuration, I see my ellipse is shaped something like this. That means I can clearly say it can apply maximum force in this direction. Okay, if at all I have to do some job, I will try to figure out, okay, this is the way I have to orient my robot to do this job in this direction. Okay, you have to tighten something, you have to press against something. Okay, so this is what you can do, this type of analysis you can do in order to analyze your robot. Principal axis lengths are reciprocal of each other. Principal axis, if this is maximum, this is the minimum. Okay, they are reciprocals of each other, and lengths are reciprocals of each other. As can be seen from the figure, the force ellipsoid has major axis orthogonal to the manipulability ellipsoid. If this is manipulability ellipsoid, this is orthogonal to that. That's all. Okay. So now there are many terms which are again associated. So few things that are takeaway. Manipulability measure 1, that is ratio of longest to the shortest axis. Okay, if ratio of this to this is one way of measuring this one. If that ratio is maximum, that means robot is reaching. If this is maximum, this is minimum, it is going to infinity, it has reached to the singular space. So that is one way of another manipulative measure. There are many other measures, so this gives you something like this. Okay. If it is isotropic, when mu is equal to 1, it is equally manipulable in all the direction. Okay, major and minor axis both are same. Higher value would mean robot is more closer to singularity. You have seen just now, if it is infinity, it is singular. Okay. So higher value would mean it is more near to singular. It is least manipulable also. Measure 2 is something that looks like this. These are defined in different journal papers. Okay, it is nothing but it simply took square of this, and that also can be used. In that case, you need not to take square root of two terms. Okay, you can simply take square of this, and this also is can give you picture of this in similar manner. It is nothing but same this square. Okay, again ellipsoid is this ellipsoid manipulability measure 3, that is another way you can measure. It is by measuring the volume of the ellipsoid. Okay, again if you don't know, I should tell you that is nothing but product of all the values, eigen values, square root of that. You can quickly get something like this and this, and that is manipulability ellipsoid. So what effectively this is mathematically it is equal to volume of the ellipsoid. So you see, this is again related to the volume. So again you see, if it is fully stressed, volume becomes equal to 0. That means it is again reached the singular. So expressing same thing in different manner. Sometimes we say ratio of these two, or square root of the ratio of these two, or you can say volume of this. If volume becomes equal to 0, matrix is singular and robot is not manipulable. So this can be defined in multiple ways. These are some of the ways. Different journals have even different definitions now. Okay, maximum volume occurs when axes are equal. That is, a sphere has the maximum volume. Okay, and that is when all lambdas are same, and that is what gives you the maximum volume also. Okay, and then it is best possible optimum condition for the robot also. Okay, so this is how it look like. Okay, so yes, there are different ways to say same thing. Okay, and there are some mathematical interpretations to what we see in day-to-day life. Okay, that's all. I think there are some notes to this type of ellipsoid. In case of orientation, you can form a different type of. So far, we are only concerned with linear velocity and forces. You can have manipulability ellipsoids even in terms of angular velocities and moments. Okay, so that could also have been dealt in similar manner. So I have skipped this for now. I have used only JV terms, not the J omega terms. Angular velocity I haven't considered, but that can be analyzed in a similar manner. Okay, exactly the way we did it. Okay, so if you want to see how manipulable I am in orientation, you can always do it. Okay, that's all. I think it is quite exhaustive with this. I would suggest you please go with this thoroughly once again. This video, play once again. I'll share you this slide, and then hopefully you can understand it. That's all. Thank you.